the geometry of strange attractors. This is in chapter 12, Strogatz. So one of the things that comes up, and that's kind of mysterious about these attractors, is we say, for example, the Lorenz system, that three-dimensional Lorenz system, the volume has to be shrinking. All of the chaos on the Lorenz attractor is happening in a bounded region of space. And yet we say there's a positively operative exponent. So that means the distance between trajectories is growing exponentially. So how can this happen? How can things be expanding into a bounded region? How to expand endlessly in a bounded region? There is an answer, and it's this phase space view of what's going on. So one of the main mechanisms, and it's been seen in all kinds of systems, is you get repeated stretching, folding, and reinjection. And it's not that in the differential equation, these phases are all distinct. It's just our conceptual way of trying to understand overall what is happening. So it's probably useful to do a cooking example, like making a croissant. And I just happen to have dough, Play-Doh. So think of it in terms of cooking, making a pastry or a croissant. So we start with our dough, and then I flatten it and I stretch it, flatten in some directions, and I stretch in others. So here's my piece of dough. It's not exactly a square or rectangle, but right, with a rolling pin, you would stretch this. You're flattening in others. And if we're making a croissant, right, it's made of, if you've had a croissant and you slice it, it's made of many different layers. So we would now fold it. So we then fold, and I'll fold it in my picture this way. And then you re-inject, right? I put this back, and then I do the same thing. I stretch, fold, and then you get all these layers showing up, right? So you re-inject, and maybe you could imagine what's going to happen at the next iteration of this pastry map. If I flatten and stretch and fold, what am I going to get? Repeat this over and over, right? What do I get in terms of a cross section? I've got two sides, and then now that doubles again. I've got 1, 2, 3, 4. It seems like I'm doubling the number of layers each time. And imagine what's happening to particles in the dough, right? If I had some particle that was here, and then some other neighboring particle here, after all of this repeated stretching and folding, they could end up almost anywhere along here, even though they started out together. So you could think of this as, at least in this pastry map example, this is a procedure that would produce chaos. 2 points starting together by repeated stretching and folding could end up anywhere in the dough, right? And we could do this more carefully. So for this pastry map, what's going on? If we start with a rectangle, and I'll call the corners A, B, C, and D, then after one iterate of the map, what will happen? Let me draw this shape. It looks a bit like a horseshoe. A goes over to here, C, D, B. And if I just keep doing that, over and over, let's call this S0, and I'll call this S1. If I talk about S2, it looks something like this up above. And now it's hard to even track what the points are doing. I do this again, and so you see this repeated stretching and folding pretty quickly is leading to some interesting looking stuff. And you could just imagine this continuing. So now try to picture what the limiting set looks like. It's going to look like a Cantor-set of lines. If we don't include the folding, that's pretty terrible looking. Just looks like a bunch of parallel lines. If you were to take a cross section through it, right, it's going to look a lot like some kind of Cantor-set. It's going to have a fractal structure and chaos. So this mechanism of stretching, folding, and reinjection and repeating, this is an engine of chaos. And maybe this seems contrived, but you can see this in actual systems. So we will look at not the Lorenz system, We'll look at a simpler version, which I think gives the idea of this. I guess this being a pastry, this would be some kind of flaky layered structure. And there's this system that we've talked about before, 3D ODE system, the Rössler system. We'll look at the Rössler Attractor. Remember, this was the one that's simpler than Lorenz because it only has one nonlinearity. And the story of how it came about is that I think it was published in the mid-1970s. Rössler was at a carnival and saw how they were making taffy. So you've probably seen taffy-pullers, right? They'll take taffy and then these mechanical things stretch it and fold it and bring it back on itself. And this made Rössler think of, I wonder if I could come up with some ODE that does this. So it wasn't motivated by some physics question like Lorenz was motivated by the atmosphere. It was just, could I come up with something simple that does this stretching and folding? So this is the model. We've seen it. X dot equals minus y minus z. Y dot equals x plus ay. And so far, everything's linear. Then z dot is b plus zx minus zc. So this is the only nonlinearity, the zx term. The typical parameters that are used, a, b, and c. A equals b equals 0.2, and then c 5.7. And just like with other systems, as you were to change some parameter, you'll see a bifurcation structure. So these sets of parameters are in that part that does give rise to chaos. So I'm going to show you what the attractor looks like. So this is an X, Y, and Z space. I think things are going this way and turning around. And the red dot, I think it's just the origin. But you can see something weird going on, right there, where it seems like trajectories from up above are merging with trajectories that are on the XY plane. So, what's the deal? Here's another picture of it with lots of different trajectories. And you can see this structure. It's different from the Lorenz attractor, but you've got things that are going up and then they merge back. So we're going to try to understand what's happening to trajectories here and see if there's a connection with stretching and folding. And there's a really good series of books which talks about this. And I found out about this, I guess, early on when I was an undergrad and was kind of enchanted by these books. It's originally started out as a set of 4 books by Abraham and Shaw. Ralph Abraham, who did a lot of work with my PhD advisor, Jerry Marsden, and Christopher Shaw. Christopher Shaw was the illustrator. So this has no equations. It's a set of books with no equations. It's just trying to explain this newfangled topic of chaos and dynamical systems, because they were published, I think, in the early 80s, just using pictures. So you might even find it. It's actually now in one book. It's called Dynamics, the Geometry of Behavior. I have it. You might notice this picture up here, like, hey, what's that? This is showing an artist's rendering of the Rössler attractor. So we're going to take a tour through what this book has to tell us. This is showing the Rössler attractor for that set of parameters that I was showing. So you can kind of see the trajectories are sketched on here. Am I able to draw? Let's see if I can. I think I can. Right? Like if you've got something, if you've got a point here, I want to make this like a lot thicker. There we go. Okay, good. Then you go this way and it goes around. If we could get that out of the way, it might be easier to see. There we go. So it goes up here and then we're kind of flipping to the other side. And now we're over here on the inside, and then this goes over behind there and so on. So let's just take that as a given. Let's say, all right, this really does represent what trajectories are doing. What can we say about it? This is starting with a patch at X here. So here's X, and this is showing what the ends of this blob of initial conditions are doing on the attractor. right? This one is going, this side is going up this way. Let's just follow it. And now it's over here. So what was on the right side is now on the left side. And if we were to track what this color, right, follow it around, it's going and then sort of merging with the part in the XY plane over here. So there's a flipping, but the main thing is this thing stretched a little bit. It got stretched at least in one direction. So, okay. Now if we take the new blob and say what's happening to it. So here's the new blob and then follow what happens. Maybe I'll use this color. Okay, let's follow the left side of that. Goes up and around. And we're over here. It flipped, and this point down here, what's it doing? Goes up and around. We're sort of sketching, comes up, goes up to the top. So we're getting stretching in one of those directions. We're also getting flipping, but the main thing now is stretching. So we call this R prime X. This is R prime prime X. I guess X was the initial blob. And this is just showing if we were to repeat this multiple times, what would we get? So we have that originally we had this blob. This is at time, t0. And then after going through this thing once, now we're here. And then now we're here. So there's this stretching. And due to what happens when you get near this fold, there's also folding. So there's stretching and folding going on in this attractor. If you were to look at what's the phase space doing, there are directions because the Rössler system, at least for this set of parameters, volumes are shrinking. So it's volume contracting. So there'll be directions in which things are shrinking and the direction in which things are stretching. There's more shrinking than stretching, but there is still stretching. So if we just look at the directions in which things are stretching, think of this as on the Rössler attractor, we have trajectories that are spreading away. In terms of like the steps that produce it, start in the upper left with this number 1, and things will begin to, due to the Rössler attractor, they're not only stretching away, there's also this curving back. And then look at this step up here in the upper left. It's curving back. It hasn't yet come back to itself, but you can already see right over here on the left that we have what was one curve, like that kind of pastry map, we've now folded. So there's stretching and folding. And then down here, when you kind of show this, it looks like it's coming back. Now they can't technically exactly merge. The two sheets are sort of just getting compressed down near that one sheet. And this is happening over and over again. So in some sense, the attractor is always just an infinite set of these sheets, which I know is odd. It is what it is. So here's another view, right? You stretch, you take one line, it stretches. So the sheet folds back on itself after one iterate. Now that curved sheet, it stretches again, and you're noticing this is looking a lot like that pastry map. You take that and stretch it again. This is what's happening. I mean, it's being exaggerated by the artist rendering just so you could see it. So if we were to take a slice through this, this would be called a Poincaré map, if we were to name it, or a Poincaré section. And then they've added in here, if you were to take a section of that section, the book is calling this a Lorenz section. And what would you get if you got this Lorenz section of what looks like an infinite complex of surfaces? Well, maybe by now you can guess a Cantor-set. So we have what appears to be a Cantor-set of points that just arose from the dynamics of an ODE on an attractor. So just reminding you, right, here's the construction of the usual middle thirds Cantor-set, where you remove the middle third. Right, there's other types of Cantor-set. It's not just the middle third that gets the name. You get this set of points that are fractal. So that hopefully illustrates what's going on there. This stretching and folding, that's the engine. And then re-injection is sometimes implied. You'll see this phrase, though, stretching and folding quite a bit. So these are at work in attractors of ODEs. And maybe you see the connection with maps. What I was doing, the pastry map was literally a map. It also maybe makes sense of what the logistic map was doing, where we took the interval from 0 to 1, and the logistic map literally, right, it's taking that line and saying, okay, I'm going to stretch and fold. It's there in the picture of the unimodal map. You stretch and fold. So now we have a way to understand it in maps too, even 1D maps. So this stretching and folding is a big theme. I wouldn't say it's the only thing that gives rise to chaos, but it is a recognized mechanism of what is going on with the phase space. We'll look at another system that shows this. It's more careful than the pastry map. We're going to call it the baker's map.